The first case shows how Expert A analyzed the relation between brain regions. To simplify narration, we use some abbreviations. EA for Expert A, C for the control group, and A for the alcoholic group. The dataset is collected from 64 electrodes. Here is some essential domain knowledge. AF7, FP1, FPZ, and FP2 are involved in this case. We can see that FP1 and FP2 are symmetrical. Besides, AF7 and FPZ are close to FP1. Expert A loaded the data and adjusted the global settings, including box length and sampling length. Since FP1C and FP1A seemed too different, she first queried the electrodes correlated to FP1 in the common group. She created 2 timeboxes, identified one timebox as FP1C, and kept the other as default. Then she selected the correlation to link 2 timeboxes and set threshold according to her domain knowledge. The results displayed 3 time series, which were reasonable. As FP2 and FPZ were in the same region with FP1, while AF7 was close to FP1. Furthermore, EA found that results with high matching scores of AF7 were mostly in the right peak segment. This phenomenon inspired her that the effects might vary in the peaks and the troughs. Therefore, EA filtered the results and discovered that the distribution of all matching results shifted to the right, indicating that all 3 pairs were seriously affected at the peak. She concluded that these 3 pairs of electrodes show synergy to the stimulus and the peak might represent the response. Next, Expert A queried how the correlation between FP1 and other electrodes decreased after drinking. She created 2 timeboxes, one labeled FP1A, linked them with the correlation, and set a reverse match to query results with low correlation strength. Then, EA added the meta-relations requiring for time series from the same electrode. EA found that the 3 pairs were still in the results and FP2 was affected the most. EA observed several results and explained that some asymmetrical effects were caused by the alcohol. She further analyzed whether there was difference between the peak and the trough. She checked the distribution of results with high matching score in the FP1-FP2 pair and found that the peak region was highlighted. The other 2 pairs had the same visual pattern, which revealed that the peak region was affected the most. EA observed time series found that the peak appeared delayed in the alcoholic group. EA summarized that the decreased correlation and delayed response indicated that alcohol could affect our balanceability and reaction speed. The second case displays how Expert B explored the relation of air pollution between cities in the North China Plain. First, EB queried how air pollution spreads from the surroundings to Beijing. EB added 2 timeboxes, labeling the second one as Beijing, and selected causality to connect them. He then dragged the second box to set the delay to around 12 hours, depending on the wind speed. EB then sketched a rising trend according to the dashed guidance lines. In total, there were 237 results. EB found that Beijing was most affected by the surroundings in May and October. There was a high causality between multiple sites in Beijing throughout the year. EB observed that Langfang was the only city located in south of Beijing, while all other cities were situated in the north. This means that Beijing has been more severely affected by air pollution from the north than from the south. EB then queried how Beijing's air pollution had spread, so he adjusted the current query. There were 843 results in total, which was nearly 4 times more than the last query. The peak mainly occurred in February and April. In the end, EB explained that with some effective environmental governance measures, such as the use of new energy, the current source of air pollution has mainly become urban traffic pollution, making Beijing a primary pollution source. EB found no cities in the west of Beijing appearing in the results, suggesting that pollution from Beijing hardly spreads to the west. EB explained that the western mountains block pollution from spreading from Beijing to the northwest regions with higher elevations. EB was interested in the differences between patterns of air pollution propagation from Beijing to different directions. He created 2 timeboxes, labeled Tianjin and Baoding. To compare these two propagation patterns, AB grouped two subgraphs involving Tianjin and Baoding, respectively. First, AB clicked on the column header of Beijing and Tianjin to combine them. Then, he filtered the relation column to explore the time fragments during which Beijing affects Tianjin seriously but not Baoding. He found that Tianjin was mainly affected in spring and hardly in summer. EB repeated the filter interaction to investigate how Beijing affects Baoding. He observed that the results were also predominantly distributed in spring. However, Baoding was affected almost throughout the whole year, while Tianjin was hardly affected in summer. EB explained that due to monsoon factors, the wind blew from Tianjin to Beijing in summer, so there was less pollution. EB investigated the chain of air pollution propagation from northwest to Beijing and its effects. He modified the query and clicked the guidance icon to find possible effects. He ordered recommendations and found Yantai had the highest average strength with the highest confidence, so he added it. The distribution showed that cascading air pollution patterns mainly occurred in April. EB inspected several results with the highest matching score and found that they aligned with his expectations. These findings suggest the possibility of long-range air pollution transmission from Zhangjiago to Yantai in spring, emphasizing the need for preventive measures and timely warnings.